Hello, Zoom people. All right, so the automatically recording. All right. Screen, desktop. Just a heads up for anybody watching on Zoom, I will not be monitoring chat, but your chat messages will show up on screen probably. If you want to throw things in the Discord, you can feel free to do that. And eventually I'll get to them, even if I don't get to them during class. Okay. All right, so let's go ahead and get started today. Yes, for the first time, I am streaming this live on Zoom. In case you didn't see that message on the Discord, you can find a link to the Zoom on eClass in case you'd like to do that instead of this. I will say that I am going to mostly be able to interact with you if you are here, unless we get to the point where everybody's on Zoom, and then it will be me interacting through Zoom. We'll see, you know. Again, this whole semester is a bit of everybody's sort of making it up as they go along. And all I can ask is your patience. So today we're going to be covering greedy search and path networks. This is going to be the second spatial representation that we are going to cover in this sort of early section. And then the third, nav meshes, which is the important one, is going to come on Monday. On Monday, I will also release a helper video for assignment 1. That helper video is going to be just a general coverage of assignment 1 with a little bit more detail, talking a little bit more about like the structure and how I'd recommend trying to start assignment 1. And I will also be waiting till Monday because the extra credit is all NavMesh stuff. So I can't talk to you about the extra credit like at all until I've given you at least Monday's lecture. That's why that's the delay. But I wouldn't worry too much. The assignment is set up where once you get Unity working, which is its own challenge that I think some of you are already experiencing, and I do apologize for that. But once you get Unity working, the homework should really only take you like a few hours. You're finding that it's like taking you way, way longer than that. Seek help with one of the TAs or myself. I'll be announcing the office hours for the TAs and myself next week. Technically, they'll be starting next week, but my office hours will just be noon to 1 on Friday, so directly after class. So if you just want to like follow me after class to my office and you want to chat there about the assignment and how it's going, that's perfectly fine. Okay, cool. A few other assignments, or a few other announcements rather. As I mentioned, yeah, assignment 1 is released on Wednesday. It's due next Friday in case somehow you missed that, or if you join the class, because I know that there's a whole bunch of shuffling in these first 2 weeks. As I said, hi, yes, streaming on lecture on Zoom. Oh, right, we're doing a practice quiz today. There's not going to be any of the, what I call like the make your own questions in this one, but all the setup otherwise is going to be the same. So there's going to be things where it's going to be like, hey, given this map, this game map, or this grid, answer these questions. The difference between the real quizzes is that I'm going to have you all produce those grids yourself and produce those things yourself. And that ensures, or at least minimize the chances of cheating. Or at least if you're cheating, you have to be cheating at the understanding what's going on level, not at the sharing answers level, which is really all I can do. But also, please don't cheat. It just is a headache for me. Okay, there's one thing that I want to say, because I got a couple emails on it, which is a clarification on the expected programming experience in the class. So first of all, you are going to have to program in this class. All the assignments in this class are programming. If you were thinking that you could get through this assignment with no programming, I'm sorry, it's just not what this class is. That's the sort of text that I'm just grabbing from the syllabus. Now, I know that several of you have no experience programming in C#. I'm not going to teach you how to program in C#. It's the expectation that you can pick up the things that you need from the documentation that you're given. Now, if that freaks you out, I would just say you can relax a little bit because there will be more structure coming in terms of trying to help you at least with the particulars of the assignments. But this sort of thing of saying like, hey, here's a code base, here's some script, this is much closer to your experience if you were, trying to program the AI for a game where you're just going to be thrown into an environment and asked to figure it out. So that's sort of the thing that I'm simulating here. This is also not an intro class, so I'm just not going to be teaching you programming. I'm going to expect you all to know how to program. You just need to be able to, sort of pick up the particular specifics of this new language. Okay? And I will be helping out more with that. That is coming, but it's not going to be a full like 101, how do you do C# programming? Okay? I just want to establish expectations so that nobody goes, wait, hold on. I thought that we were gonna, be taught what an if statement is. That's obviously what nobody is going to be saying, but this is a one extreme. Okay, so last class, if I can click, there we go. So last class, we did an introduction to grids, their pros and cons, and we did an introduction to assignment 1. Again, yes, I'm starting office hours next week. Expect an email tonight. Expect an LPR video Monday. Again, we have the lab in person on Thursday. The lab is just in-person help. You do not have to attend it if you feel you do not need it. And also, please do not cheat. Though again, for this first assignment, because the code is so similar, you can do this assignment in 3 lines of code. There's not really anything I can do to ensure that like people's lines of code don't match up. But as we get through the semester, more and more of the assignments should look distinct. And if they don't look distinct, if there's big chunks of code that are copy and pasted between people, that's going to be an issue. So please don't do that. Just please don't share code. I don't mind if you talk to each other about your assignments, that's fine. Just please don't actually like copy and paste code to one another, okay? Cool. Okay, so on Wednesday, we were talking about greedy path search, right? I gave you a very, very high level notion of how would you greedily move through a grid, right? And we talked about how where that could be good in cases like this, and where it could be bad in cases where we have obstacles which are going to sort of trick the greedy path planner. But what I didn't do is I didn't explain, hey, how does this greedy search actually works in detail? And so that's what we're going to talk about today, because it's going to be necessary as we're talking about the sort of future spatial representations to talk about, hey, how is an AI even going to move through a space like this? So greedy search path planning, here's the way it works. Step 1, if the current grid cell is your goal, congratulations, you're done. No worries, yeah? That's the easiest kind of search there is. So this is the equivalent in your Unity project of you clicking in the same location that Pac-Man's in. It's just done already. There's no need to do anything else. No problem. 2, check each unchecked neighbor grid cell of the current grid cell. That's your second step. So, okay, if we're not in our goal, let's check if any of those nearby ones are our goal. This should be pretty easy, right? You just got a for each loop or a for loop. We're going to iterate through all those nearby ones. We're going to say, hey, is any of these the right one? If none of these are the right one, we want to choose the closest grid cell to the goal according to some heuristic, okay? Heuristic takes in, an X and Y position and has a notion of the goal. And that's going to tell us the next current grid cell. Generally, the heuristic something is like, the shortest distance. So whichever one of these has the shortest distance to the goal, that's the next place we're going to go. And then we're going to set the previous current grid cell to this current grid cell's parent. This is important as like a bookkeeping thing, which is going to be helpful for finding the path once we do find the path, if we find the path, okay? Finally, go back to 1. And this is just the loop that you're going to iterate through. Now, you don't have to write this loop yourself because, again, the way that game engines work is that they have update functions. And that update function is going to be called every frame. So instead, what you can do is you can just have steps 1 through 3 in every single frame. Cool? All right, it's a fairly straightforward thing. Here is it in pseudocode. I'm going to walk through this at a high level. I'm not going to sort of like dive deep into every line of this, but just quickly, right? We have our current node as our starting node. We're going to while, again, this is under the assumption that we do not have just an update tick that's going to do this looping for us. But while our current node is not our goal node, we're going to grab all our neighbors. Those are all the positions nearby. We're going to then search through all of our neighbors. We're going to see, hey, which of these is the best one, the closest to the heuristic. We're going to set that to our current position. And then at the end, once we find the goal, once this is no longer not true, we're going to reconstruct our path. So this is the thing about why it was important to say, what's the parent of this node? Which is basically a way of saying, what's the direction that we got to this node from? What was the last node that we were at when we got to this current node? And that lets us reconstruct this path, which is basically to say, hey, let's start off with the path being empty. Then we're going to add the final node to it, which should be the goal node, right? Because we know that the final current node was the goal node. Then we are going to keep iterating until we don't have any parents, until we don't have any place that we were before, and add every position we were at before this one. Then we reverse the list, and then we return the path. And that gives us a final path from our starting position to the end, to the goal position, okay? Is that fairly clear? Seeing some nods. I'm also seeing something that might be concerned or sad or confused faces. It's hard to tell faces when you're in masks. If you have any questions about this, please raise your hand. You don't need to understand this deeply. You don't need to be able to implement this, but you do need to be able to understand what's happening here intuitively, right? Okay, nobody's raising a hand. Nobody's raising a hand. All right. So we can now look at this and we can actually have a little bit of a better understanding of what's happening in this figure, right? So our starting position is this red figure. Apologies if anybody is red-green colorblind. Hopefully you can still see the gradients. And the final position is down here. This bottom right position is blue position. What this sort of yellower to sort of bluer positions are the heuristic values of these cells. So the bluer it is, the closer it is to our goal, okay? And we can see that we get this gradient, right? Because it's just a straight line distance to our final goal. And that's why we end up picking the cells that we do in this ordering, because we're always chasing the one that's going to be closest to that heuristic. Does that make sense to everybody? Okay, so nods, great. I think I appreciate the nods. The nods are really helpful for me. So this now explains why this one is such a problem. While it is the case that we do finally find a path that's going to get us there, right? The problem is that we have to search through all of these positions before we actually are able to figure out this way around it. That's not great, right? That's extremely slow. There are ways around that, and we'll talk about it. But before we talk about it, let's talk about heuristics. So can I just get a show of hands who's heard of the term heuristic before? Okay, so roughly maybe 3/4, maybe 4/5 of the class, something like that. So a heuristic is just basically an approximation of some notion of distance, okay? Typically, when we're talking about a heuristic, we mean like a conceptual distance, which might be a weird thing to think about. But usually it means something like, okay, we know what the ideal would be. Okay, conceptually, we know what an ideal would be. Maybe it's the ideal sentence if we're trying to generate sentences. Maybe it's the ideal product if we're trying to generate products. Maybe it's the ideal sale if we want to try to generate a sales system or something. I don't know. In game AI, a heuristic tends to mean, not always, but it tends to mean one of two things. One is just, hey, the distance to a goal, like in a space that we want you to be in. The second one is a distance in terms of your current behavior from some goal behavior. That second one we'll get to later. That's like a few weeks down the line. Currently, though, we're just talking about the distance in terms of your current position to a goal, okay? Typical heuristics are things like straight line distance, which is literally just like the Euclidean distance. You've all had to do this before. You all know algebra, I'm pretty sure. Manhattan distance, which is just the absolute difference in both the X and the Y dimensions, or the Z or Z dimensions, if you like, as well, if you have a 3D space. In non-game AI, it's important, we'll get to this a little bit later, but it's important that a heuristic must underestimate the remaining distance to a goal to be admissible, okay? We'll get into notions of what it means for a heuristic to be admissible a little bit later on when we're talking about H-star search. But in game AI, we do not care about admissibility. We do not care about that being consistent. All we care about is how the heuristic is going to lead to behavior and how that behavior appears to the end user, okay? And with that, very first question, already, participation question 1. That's right, get out your devices, get out your laptops. tinyurl.com/does-pq3. I will, as I promised, I will just write that URL in the course Discord. Here it comes, tinyurl.com/does- PQ3, right? Yeah, PQ3. Boop. So here's the question. What I want you all to do is to list the current nodes or grid cells in order according to the given greedy search algorithm, the one that I just showed you, in the Manhattan distance. Okay? So which is the absolute value between the X's and the Y's, assuming that we're starting at A and that our end goal is F. If it's helpful, you can assume that A is position 0, 0. You could also assume that O is position 0, 0. It doesn't really matter. All that matters is that every grid cell is one apart, okay? There's a second part of this question, which is there another heuristic, not the Manhattan distance, another heuristic that could have found the goal faster? All right? just as a heads up, if this was like a real quiz question, what I would do is I would ask you personally to pick a few positions on this map to cover up with blocks like those blue blocks there. Just say those are non-grid blocks. And then you'd have to solve it from there, okay? Cool, so take a couple minutes, give that some thought, and then we'll talk about it. Okay, so let's go ahead and get an answer. Do I have a brave volunteer who's willing to raise their hand and list some letters off to me? Please.
B, C, D, S, T, U, M, F.
Nice. Yeah, that's correct. So just for the benefit of everyone, and I'll be a little bit louder, you're gonna go A. From A, our options would be H or B. B is closer according to the Manhattan distance, right? So that is 1, 2, 3, 4, 5 cells away, as opposed to H, which is 1, 2, 3, 4, 5, 6, 7 cells away. So it has to be B. For the same reason, from B, it has to be C. From the same reason, it has to be D, and then E. Now at this point, we only have one option. We don't go backwards. We can't go to a visited cell. That's per the algorithm that I gave you, though understandable if you didn't have that on screen. So it has to be L. From L, it has to be S, because between at L, we have S or K as options. K is 1, 2, 3, 4 away. S is 1, 2, 3, 4 away as well. So technically, you could say let's go to K instead, but we all know what you should do, which is to randomly decide that S is the correct one. Now, if you were a real AI agent, this is a reasonable question to have. How would you know, right? How would you tie break? Generally, either you decide to tie break at random or according to some additional heuristic or rule. So you could say always tie break, using a secondary heuristic, or always tie break by going to the right, or something like that. So anyway, let's say that we tie break by going to S. From S, it has to be T. From T, it has to be U. From U, it has to be M, and then F. Easy. Cool. So this gives you a final path, which looks a little weird. Remember talking about the duck. In this case, we're going to go right up to the wall, and then we're going to kind of like shimmy around it, like staying as close as we can to the wall that whole time. That's not a super realistic way that somebody would walk, right? If a human had to walk this path, well, first of all, they wouldn't just walk in a straight line. They'd probably walk directly from A to T, right? And then from T to U and U to F, something like that. So not great. Okay, how about the second part? Does anybody think there is another heuristic that could have found the goal faster? No, nobody? Well, you didn't fall for my trick because you're right. there's no heuristic that would lead to fewer steps than this. It has to be that many. It doesn't matter how many you're going from there. The only kind of issue is the sort of K or S situation, giving the Manhattan distance. But again, you could use a variety of sort of specializations of the heuristic I just gave you, or changes of the thing to do that. If somebody's now typing down the answer once you see this, please don't do that. Please actually try the question. You don't have to get it right. You just have to try. And then from there, the final question about like, hey, is there something that could do this faster? Is that there isn't, but you could have a heuristic that discounted any cell with an obstacle between it and the goal, which might end up looking more natural, right? So if we had a heuristic like that, rather than going from D to E, we'd probably go from D to K, from K to R, from R to S to T to U to M to F. Same number of steps, but it would look slightly more natural than like shimmying along the edge of the wall. Okay. But again, yes, please actually try the questions. Please don't wait to see the answers. That's not helpful to me or to you. And please don't write, I don't know either. Please really try. I promise that it will help with your learning outcomes. Okay. And now we get to a question. Now we get to a problem. How can we change our space representation to avoid clunky movement? In that last example, we had really clunky movement. In this example, we have really clunky movement that doesn't really make sense whatsoever. How can we change the space, not just the pathing approach, not just smoothing it later, but how can we change our spatial representation itself to avoid clunky movement? Any thoughts on that? Yeah.
Allow for diagonal movement.
Allow for diagonal movement, sure. So that'd be a simple one of saying, if we're at a grid position, we're going to have to guarantee we can always move along the diagonal. Now that might be dangerous and would actually change what cells are valid, right? But yes, you're right. We could do that and that would be a simple change. But we can still get some weird stuff happening, right? So for example, take a look at this, right? If we allowed for diagonal movement, we could potentially still do A to I to Q and then sort of go along that way. But that still doesn't look supernatural, right? But it's a good start. Anybody else have any ideas? Yes. Make the grid smaller. So if we make the grid smaller, we're actually going to get more discrete movements, right? It'll be like even quicker, like going back and forth and back and forth. So I'm not sure that would help us with natural movement. Anybody else? Yeah. Variable cell sizes. That's an interesting idea. So I like the idea of variable cell sizes. So for example, we could say this whole region is one giant grid cell. And we say, hey, that whole region is safe. You can move through that whole region safely. I like that idea. We're going to get to it. We'll get to it on Monday, that idea. But before we get to that idea, we're going to get to a slightly different version. The reason why I'm doing this is to sort of structure how we're going to talk about things on Monday, and because it matters historically. But there's this other problem as well. Let me actually stay here for a second. There's this other problem as well. So let's say that we made A to S, this big rectangle, all free space. There's an issue here, which is to say, let's say we had this as a whole big free space, and then we had T as a separate little free space, and we had this as a whole big free space. Now, if I said that was true, and I was up here at E, okay? Let's say I was up here at E position. For those of you following along at home, if I'm in the equivalent of grid cell E, and this whole region is free to move through, and if I tell the AI, hey AI, I want you to move to T, at that point, the best the AI can do is straight line distance from E to T, which is going to get it caught on the wall. Not great. So yes, for sure, variable cell sizes is going to be an important part of the solution here. But we need something else too. We need some way of telling it what are the safe places to move between these variable cell sizes. How do you safely do that? And for that, we're going to use something called a path network. Now, back in the day, we didn't even have these variable cell sizes you were just describing. We just had path networks. So we're going to start there. Let's assume we just have path networks. These are just going to be paths, which are going to tell us, hey, where's it safe to be? Instead of having cells that say, in this space, you're safe, instead we're going to have lines. And we're going to say, on this line, you're going to be safe. Okay? That's the basic difference. Typical way this works is that you have a sparse network. So you have nodes, right? And you have edges, connections between nodes. Let's pass between those edges, and we're going to often have weight of the edge, which is the cost of traveling that path. Sometimes this is equivalent to the distance, the length of the edge, but sometimes you want to have it be other things as well, to say, let's bias it away or towards certain paths. Oh, that was weird. It is going to connect, the basic idea is that we want to connect points that are visible to each other on all important areas of the map. This is going to allow us to get past that issue we had earlier about, not being able to just straight line distance from A to T. Because now we can, because they're visible between the two. This is doing some weird stuff. I don't know why this is happening. They're usually hand tailored or just straight up hand authored, or they were. Nobody does path networks by themselves now. We'll get to it. Path networks are still very much used, but they're usually not hand authored anymore, but they used to be. But they can be generated, and they can use things like FloodFill. So here's an example of a path network. Okay, so for example, if I was going from O to Z, right, we would have a 71 cost to go between those two. If I'm going from O to S, that's 151 cost. So when we're doing that same sort of greedy approach that we were doing before, instead of looking at a heuristic value to say, hey, what's the distance between these two, we're also going to be looking at, hey, what's the distance to travel between these things we're traveling on. We're going to use that to try to figure out the shortest paths. Okay. Here's a quick trick. So grids can actually be thought of as actually just path networks that are just extremely uniform in depths. Some of this will be obvious to some of you who are already used to thinking about graphs, who are used to thinking about nodes and edges. But for those of you who are not, right, it would look something like this. Now, we would never actually want to use something like this because why would we, right? We can just use a grid. Also, I missed one edge. right here. My bad. But that's the basic idea. Now, as I mentioned, you can generate them using a flood fill kind of approach. This is not typically used. Again, I have an old scan of a old game AI textbook here. The basic idea is that you want to start with a seed where you know you're safe, and then you sort of grow the graph in equal increments until you get something like this. Now, this is even more dense. There's even more edges than a typical grid, and it's also not going to be as good as like a hand authored thing. But you know, if you wanted, for some reason, you could have a path network like this. Okay. Okay, the basic idea of using a path network is that we want to find the closest visible graph node. Okay. Now this is interesting because this indicates we don't always have to be on a graph node. We can go off the path a little bit. Okay, as long as we know it's safe around that area. So if we can find the closest visible graph node, we want to immediately just go there, straight to there. Then from there, we want to find the closest visible graph node to our goal, the place we're actually trying to get to. All right. Then we want to search for our lowest cost path from A to B, move to A, traverse the path, and move from B to X. Now this is interesting, right? Because this is saying, hey, we can be off the path for the first time. We couldn't get off the path when it came to the grid. There's no way. That just wasn't possible. But now we can. And now we can go places that weren't explicitly defined. And with that, guess what? Surprise! There's a second participation question. That's right. Some days I will have multiple participation questions. So the basic, sorry, I had a person, a landlord person trying to message me. Anyway, let's go ahead and give you all, this is pretty easy, right? This is just the exact same message, but with a B on it. Exact same URL, but with a B on it. Again, please actually try. Please don't wait till I give you the answer. Basic idea. I want you to list the current nodes from calculated path from the circle to the X with greedy path planning. What is the shortest path overall? Those are two questions. Yes.
What is the weight at RC?
Mm-hmm. The weight is 1. Yes. The circle. So using this, right? From a particular starting position, we have to find the closest visible graph node. So I won't answer that because that has to do with the answer to this. But I want you to think about that line. Find the closest visible graph node. That directly has to do with these two paths. So I'm asking for two paths. Feel free to just like give me the first set of letters and then like a comma in the second or something like that. All right. So this should be a fairly quick thing, but let's go ahead and see here. Does anybody want to volunteer to give me the first part? What is the path, according to this approach, to go from the circle to the X in terms of the current nodes? Anybody willing to give me some? Oh yeah, please.
OSRC.
OSRC, correct. Well, almost. But there's one part off this. We need to find the closest visible graph node to X. The closest visible graph node to X is D. So very close. So it should be OSRCD is going to be the closest one. So that matters, right? Because what it's saying is we can't assume with a path network that we can safely move from C to X. We just can't know. But we generally can assume that we can go from the closest node to the goal position. All right. And I already put it on screen, so I'm not going to ask somebody to give it. But right, obviously, the shortest thing would actually be no or. I should ignore that. Ignore the O and the D, right? But if we cut off the O and the D, right, then we can go directly to S from R to C to X. And that would be the shortest path overall. But given that path network setup, that wasn't possible. We'll get into why that wasn't possible and what it means about spatial representations on Monday. Let's talk about some pros of path networks. They're a very compact representation at runtime. They have to actually be stored if they're authored, but at runtime, they're extremely compact, right? We just have a small set of nodes and a small set of edges, as opposed to a grid, which is many more nodes and many more edges, right? So that's a benefit. Now, if they're generated, obviously there's no storage, and it's going to be roughly equivalent to a grid at runtime. It does not require an agent to be on the path nodes at all times. This is huge. And something like, I don't know, how old ago was that? Like 30, 40 years ago, this was huge in terms of game AI to say like, hey, you don't have to be on a grid or the equivalent. You can just sort of use this path network to figure out where does the AI need to be. You can get continuous non-grid movement in a local area. So we can have straight line distance, right? In fact, it's sort of based on straight line distancing. Now that doesn't necessarily going to give you the smoothest path because we have the same kind of issue as before, right? So like, let's say there was a path network right after this table. There's a path network or a path network node right after this table, and then maybe, in the middle of that table. The best I can do is something like this, where I go like straight to this node, and I turn and I go straight to this node. Not super realistic, not super natural movement. Now we talked about path smoothing already, and that is a possibility again, but we'll talk about that a little bit later on. It also plays nice with steering behaviors. Now, steering behaviors are these kinds of notions of how do you alter the path after you've generated it. And we'll talk about that in a future lecture. The other really interesting thing is that you can indicate hand-designed special locations or nodes and paths edges. So we could do things like say, hey, you particular AI, you are not allowed to use this path because this path could indicate something like scaling a wall, right? And some AI agents in our games cannot scale walls, and some of them can. This can also allow you for things like flying. If you have flying agents, right, there's no reason why the path network has to be labeled on the ground only. You could have stuff that moves between locations like that. Or doing things like taking an elevator or any sort of notion of a specialized notion of movement that isn't just walking. So that can be possible to indicate with a path network in a way that wasn't possible before. Same thing with particular nodes, right? You cannot go to this particular node unless you're this particular kind of entity. So that's very helpful. Now there's a lot of cons. Let's see. So I'm going to end the show. I had an old video here that that somebody made private, which is really disappointing for me that somebody would do that. But now I have this new Half-Life 2 video that I had to find last night. So Half-Life 2 is one of the more recent games. Now, again, this is one of the more recent games that used a path network. That should tell you how long it's been since people just used path networks, right? It's been a while. Nowadays, everybody's using nav meshes plus path networks, but we'll get to it on Monday. Also, it looks like my camera froze, which is great. But let's take a look. Let's take a look at this advanced AI. Okay, so player is getting shot at by this AI, hiding behind this door. Go to look out, and the AI hasn't moved. No closer, staying exactly where they are. No closer, staying exactly where they are. Back and forth, back and forth. Not moving, not moving, not moving. Okay. Get a little bit further away. Oh no, what's he doing here? Gather some stuff. Oh, interesting. That's the miracle, folks. Did you know that just bottles of random chemicals can stop gunfire? I'll go ahead and stop there. So what's happening here, right? This is hackable, but it's a hackable encounter for a very specific reason. Anybody have any ideas? Hint, it relates exactly what we were talking about today. Yeah.
It thinks about chemicals in that object, so it can't interact.
Kind of, right? Yeah.
I think maybe the AI recognizing people's face that they can it can
So the AI isn't looking at faces. Game AI isn't generally playing the game like we play the game. It's not looking at the screen. It's reasoning at a different level, right? So from its perspective, it just sees a path network. Yeah. There you go. This entity, this little glass bottle, is blocking the path on the path network. Remember the rules of the path network. You can only move to places that are visible. How do we determine if something is visible? We're going to do a raycast. What gets blocked by a raycast? This bottle, for example. So this AI literally can't move any closer to the player, can't move from where they are, because their raycast is being blocked. This is the problem with path networks, that you're limited to a specific linear path, which is hand-defined. There's no dynamic things going on where we can get around things. Okay? All right. So besides that issue, loading. Getting on and off the network can be awkward, like we saw in the pathing example earlier, where we ended up going sort of further away than we needed to, or further using a weird path to get closer to something just because it was the closest node to a particular goal point. Path node placement is also really tricky. This is a big reason why people stopped purely hand authoring them. Now there's still a ton of hand tweaking of path networks. A lot of work goes into ensuring that the spatial representations of the game look right and act right. It's a lot of hand adjustments that have to be done even to this day. It's a really tough thing. It's particularly difficult for complex maps with like weird, spiky edges on them, and you may end up with invisible spots. So this one was sort of a created invisible spot that the AI just couldn't get to. In the earlier video, which is now sadly no longer on YouTube, it was a case where this AI agent was at the top of the stairs and the player was at the bottom of the stairs. And the AI agent literally couldn't do anything, could not see the player, kept on doing this sort of Mr. X thing of like wandering away because the closest path node was the top of the stairs. That's literally all the AI could do. Further, dynamic pathing doesn't work. This is the example with the bottle. We cannot dynamically path if something blocks our view. There's no way to do it. Okay? Cool. Is that clear to everybody? Everybody's basic understanding. Fantastic. So last sort of thing to talk about today before we get into the practice quiz, path networks versus grids, right? Who wins? You decide. There's basically situations where you might want to use both. So in terms of memory, right? Do we care about on-disk memory or do we care about runtime? Now, these days, we don't care about on-disk memory at all. But in the past, once long ago, we cared about on-disk memory. And for certain specific, special sort of cases, like specific custom handheld devices or something like that, you might care about on-disk memory. So a grid takes up no on-disk memory, right? Because it's just basically the algorithm to generate the grid. Path network, on the other hand, is going to take up on-disk memory, unless it's generated, and then also none. At runtime, a grid's going to take up much more memory than a path network, both because you have to store the grid, but then also there's a lot more computation you have to do with the grid than with a path network. And so that's going to be an issue for your runtime costs. In terms of game design, we talked about this a little bit already, but certain kinds of spatial representations support certain kinds of game designs. Like a grid makes sense where we have to have discrete positions where things are in, like a tactics or a puzzle or things like that. Or like a design game, I think we talked about before, the type of computation. So this gets into notions of basically where do you want the computation to have to be. So for a grid, there's very little computation when you start, right? It's basically the code to generate the grid, no problem. But then when we're actually running it, where's the computation going? If we have a lot of pathing that needs to occur, a lot of like very tricky pathing that we need to constantly be evaluating, the grid's going to take up a lot of our memory. Versus a path network, because of its structure and it's much more sort of sparse, much less at that point. And then desired agent behavior, right? What do we want the agent to look like? So all of these are the sorts of questions that you might use when you're trying to decide between these two. But again, these days, really you're deciding between nav meshes and grids and some other specialized representations that we're just not going to get into, that we might just around. So summary, path networks probably feel like a weird in-between approach because they are a weird in-between approach. And on Monday, we're going to talk about nav meshes with all the benefits of path networks and more. And this will give you everything you need for homework 1. Okay, so it is practice quiz time. Again, this is a practice and will not be graded. You'll note that PQ can stand for participation question or practice quiz. Ooh, that's intentional. So it's really just about saying, hey, you tried. That's really all I care about, that people genuinely try. Oh, here we go. Yes, sorry. I was like, hold on. Why am I talking about answering the questions? Right. So I can, if you have a question, feel free to raise a hand and say like, hey, what's up with this particular practice quiz question? I'm happy to do that. But please don't ask a question in a way that gives away the answer. All right. And then finally, you may use notes, slides, or videos, whatever you want, but I prefer that you not talk to your fellow students. So I'd ask that everybody basically stays quiet during this unless you're asking me a question. Okay. This is only designed like for questions that'll take you like the last 10 minutes of class. Will probably end actually like after 8 minutes, so I can go over the answers with you. Okay. Any questions on the general format? Okay, then with that, everybody load up the practice quiz. Unlike earlier, the all the questions are basically full text given to you. I will also, once again, put it on the Discord, but hopefully at this point, everybody's sort of gotten the basic structure that I use for all of these hyperlinks. Quiz 1. Okay, that is now on the Discord, and here is the quiz. Probably about 3 more minutes, folks. Does anybody need more time? Show of hands. Okay, give 1 more minute. Yeah, feel free. As a reminder, you have 48 hours for all in-class stuff like this. So don't go thinking like, oh no, if I don't do it in this next minute, it's the end of the world. Okay. Apologies if you're still working, but I want to make sure that there's time to go through these questions real quick. So, which of the following best defines game AI for this class? A, pathfinding, no, right? Can't be that one. We already talked about how it's beyond just pathfinding. We talked about things like PCG, we talked about things like data science, etc. B, NPC behaviors, also no. We talked about it's the things like generating out the whole content. A, B are inclusive. If there was like a D, all of the above, yeah, no problem, right? Easy peasy, include those, but not A or B by themselves. C, non-human game development decisions. Interesting, let's get back to it. D, non-stochastic decisions in the game. Now they're going to be randomness. We already talked about it. In fact, today I talked about it. If we are deciding between 2 possible options, right, there's randomness generally. So it can't be non-stochastic. And then decisions in the game, that's not sufficient because we also talked about data science, which is outside of the game. So C, now the wording here could be better, and I do apologize for that, but non-human game development decisions, if we're talking about game development as inclusive of things that are in the final game, then yes, that is everything you want, and we're going with C, okay? That's the reasoning there. 2, for the environment to the right, would you use a grid or a path network? Why? Does anybody want to volunteer to give an answer here? Please.
I would use Path Network because for grids you would have to check like so many edges.
Yes, that's fair. Does anybody have a suggestion for why you would want to use a grid for this? Oh. Okay, so what I'll say is that for this one, I would have accepted path networks or grids entirely based on the why. For questions like this, I really do not care about the first part of your question. I only care about your justification. So make sure you include a justification for these kinds of questions or you don't get points. But for the grids, right, you could say something like, well, let's pretend that we are doing a puzzle game. If we're doing a puzzle game, like, yeah, okay, we should be using a grid for this. 3, for the grid to the right, which grid cells are valid? Blue blobs are obstacles. We're gonna go through this really quick. 1, valid? 2, valid? 3?
No.
Right, we're not gonna do 4, there's not even points. 5, valid? 6, valid? 7?
No.
Correct. 9?
No.
Right. 10, 11, 13, and 14, all no. Which is this with 11, 12, and 15, which are all valid. So just to be clear, 1, 2, 5, 6, 11, 12, 15, which means it's not possible to get between these 2 sections of the grid. I sure hope that there's other places we can go to in this game. Finally, Let's say we have a game with different grid cell sizes. Some grids are twice as large as other grid cells. What would need to change in terms of generating and using the grid? Well, basically you need to check your corner cases and you need to check your path planning. Those are basically the two things that we need to change. Full answer is here, which will be on the PDF. There's lots more things that you could have said for 4. You definitely should have said that the validity check would be unchanged. That's wrong. But otherwise, if you said any sort of collection of these things, you're good for that one. All right, we're at time. Thank you all so much. As a reminder, if you want to hang out, follow me to my office. I'll have my office hours directly after this, or my office hour directly after this. And otherwise, have a great weekend. Bye, everybody on Zoom as we reach the end.